and I'll be presenting today on the fundamentals of accuracy and precision. We're going to be operating in 4 parts today. This is part 1 of 4. And if you haven't caught on already, this is intended as a part A, really, to go with the part B that Corey Allred will be presenting in an afternoon session tomorrow. So please give that some consideration as a follow-on to these 4 sessions. These are designed to complement and prepare you for being successful in Corey's seminar as well. We need to start out with a fundamental truth that as surveyors, we've all heard, but it definitely bears repeating. And that is every measurement contains error. And why is that? Well, the reason simply is that all our measurement devices are created by humans. And we have always chosen to, how shall we say, stop before perfection. In fact, philosophically, perfection just isn't within our grasp. So we build every measuring device to an acceptable level of error. Okay, so there is error in the creation of every device, and there is error in the use of every device. Well, therefore, no matter what, we may think we've got wonderful equipment, but it always contains error. I'm going to be a little bit old school here, and I'm going to comment, not complain, but I'm going to comment from time to time about what I perceive to be issues within our industry. And right now, when I troll around on online groups that, like, there's a couple of Facebook groups that are kind of host to field crew discussions, what I see is a lot of people are very impressed with their equipment and have no idea of the inaccuracies associated with those pieces of equipment. Now, some are very good, but that doesn't necessarily mean we don't think about error. In fact, I'm going to go so far as to say that for every competent surveyor, the first two priorities when measurement is about to take place go in this order. First is error management. Second is the measurement itself. And what do I mean by that? Well, first of all, the idea of error management coming first means that before you undertake any measurement, you are considering what are the potential error sources and what are the limitations and capabilities of the equipments and methods you're using. If you're not aware of those, then you're probably dangerous. So once those are well in hand, then it's time to make the measurement process go forward. But even then, once you've got those results are limited by the error. And we'll see here later in this 4-part series that once we have a measurement, there is an uncertainty statement that goes with it. And some people aren't really comfortable with that term uncertainty. And we'll comment on that more and more as we go. But there is uncertainty, and that uncertainty, often we're referring to it as error. Error here is not like baseball where it's a blunder. It's a difference between values, and we'll explain that here in a little while. In fact, that little while has come. The error, an error is the difference between an observed or calculated value and a true value. Now, let's go back to this concept of all measurements contain error. Can we really know the truth? Well, no. We can estimate the truth. We can get fairly close to the truth. So what we have to settle on as being a true value in I believe all, if not nearly all of our cases, What we have to settle on as a true value is really a mean or an average value. So we're going to see that borne out when we do standard deviation computations in a little while. So an error is the variation in our measurements, calculations, or observations. And sometimes that's due to mistakes. Sometimes that's due to uncontrollable factors, or it could be to controllable factors. So we'll split this down even further here in a bit. Well, the title of our seminar here is The Fundamentals of Accuracy and Precision. And those terms get used interchangeably, usually due to carelessness or sometimes just due to a misunderstanding of their difference. So I'd like to dispel some of the misunderstanding by starting out with the definition of accuracy. And that is, accuracy is the agreement between observed values and the true value. In fact, it's a measure of results. If you are some kind of target shooter, whether you're using firearms or you're a bow hunter and you're practicing, you like to hit the middle of the target like we see here. And in this case, you would be accurate. Why? Because you are hitting where you're aiming. Okay, we'll see some variations on this graphic here in just a little bit to illustrate a point. Precision, by contrast, is agreement among the readings of the same value. That is, we measure our methods, not our results, but our methods. In other words, here in this graphic, I'm not only accurate, but I'm also fairly precise. That is, I'm aiming for the middle of the target, and I'm hitting all the way around in the inner circle, really. But I'm also precise. Why? Because my hits all form a tight little group. Now we'll see here in a little while that we can have a group that is rather spread out. So I could be very accurate, yet imprecise. I could be very precise and yet inaccurate. So there is a difference. Another way of saying it is accuracy is how well I fit the truth, and precision is how well I fit my own results. Okay. Precision is also has to do with the spread of our data. Now, before I start splitting accuracy and precision down even further, let's talk semantics here for a bit. And that is, the terms accuracy and error are often used to describe the same condition, but from opposite perspectives. It's kind of is the glass half full or is it half empty? Well, the answer is yes. And those two conditions, those two descriptions really relate to one condition. So when I say accuracy here on this page, we could also substitute precision in there as well. That is, as error goes down, precision goes up. As error goes down, when we're talking about accuracy, accuracy goes up. So you'll see this kind of coming out in our conversation, and especially when you start to deal with understanding the documentation that will come along with, say, least square software, or even looking at some text, reliable reference source on error and accuracy and surveying measurement. All right, this particular graph is all over the place, and I've simply reproduced it here. And let's talk about this just a little bit here. On the vertical scale, we have accuracy, and accuracy increases as we move vertically going up, and then precision increases as we move across the chart from left to right. So in the lower left condition here, I've got a target and I've been aiming at the middle of the target, but clearly I'm not hitting at the middle of the target. In fact, what I've got is a rather scattered group down and to the left. Now, some of you who are veterans may remember very well being on the range and being told by the range officer, okay, you need to go, up 2 clicks and right 1. In other words, you're being told to adjust your rear sight to improve your sight picture, or to get your results to hit where your sight picture shows you. So when you do that, when you fix the sight on your weapon, what you're doing is taking care of a systematic error. That is an error that can be fixed or eliminated using the concepts of physics or mathematics. So once you do that and you replicate the same effort, you'll get what we have here at the upper left, where now you're aiming at the middle and you're getting the same scatter, but it's centered on the middle. So what have you done? You've improved accuracy, but you haven't improved precision. So in order to improve precision, again, if you're a veteran and if you remember those times on the range, well, then you were asked to work on your position, your breathing, your trigger pull, a variety of things, your follow through. And what you ended up doing was improving your methods. And as a result, your group got tighter, didn't it? Well, what you did was you added to your improved accuracy, improved precision. Now, if you had not taken care of the systematic error, but you did take care of the precision issues, then you would have gone from the lower left to the lower right. You'd be precise, but you'd be still inaccurate because you're not hitting where you aim. Now, bottom line, we are intending in our measurement work to decrease uncertainty. Decreasing uncertainty. So we want to go from low precision, low accuracy to high accuracy, high precision. Now, let's distinguish between a mistake and an error. A mistake really is a blunder. Now, some of you think, "Oh yeah, I've got a blunder. I make margaritas and daiquiris in it, right? Daiquiris, excuse me." No, it's a different kind of blunder. This is a mistake. And you might say, yeah, I've made mistakes with my blender too. Well, okay, it's a type of error if we're being loose in our definition. But if we're tightening up our definition of error, this kind of blunder is something that results from carelessness or misunderstanding or some kind of poor judgment. You misread the tape, you misread the rod, or you're writing something down and you transpose some numbers, or you fat finger something on a calculator. That is a blunder. It's not an error, it's a blunder. Why is it a blunder? Well, you don't know that you've done it. If you knew that you were doing it, you probably wouldn't have done it, right? So please understand that mistakes, and we'll talk about these more later, we work to eliminate those, and we effectively throw them out of our data when they do occur, so they don't taint the rest of the data. But an error really is the difference between a measured or calculated value and the true value. And in a lot of cases, the true value is going to be the mean value, okay? So systematic errors, as I alluded to just a little bit ago, are errors that conform to mathematical and physical laws. That is, they can be measured. We can figure out what they were, like in the aiming at the target example here in a little bit. Range officer tells you go up 2 clicks and right 1 click. Okay, why are they doing that? Because that is known to, at a certain distance, produce a known offset on the target in the conditions at hand. So we make those corrections, and lo and behold, we find that we have eliminated the systematic error. Also, these have a positive or negative value. There's a difference here if we were going up 2 clicks and right one, or down 2 clicks and left one. So just like we can do that, we could have some kind of error. For those of you who are old enough who remember doing taping and doing temperature corrections on your tape, it depends on if you're above or below 68 degrees, which is the standard temperature for calibrating tapes. So you had to pay attention to which way am I correcting. Now we can either determine what the error is and eliminate it, or we can live with it and then correct it, like we did with tapes. We didn't go out and heat or refrigerate our tape so it was always exactly the same length. We had to correct it. So here these days, in more modern days, one of the most common ones that's really easy to do, it's a blunder that we do it, but it is known in terms of its size, and that is an incorrect prism offset. A lot of us use prisms where they're either 0 or 30 millimeters, but some of the companies like Leica will use a different offset, like a 34 millimeter offset. And if you don't have it right, you're going to have distance errors. Something else we can deal with is not taking care of the EDM settings to accommodate for temperature and pressure. Or, oh boy, we've all been bitten by this one, a bad rod height. Whether you're talking GPS or total station work, a bad rod height, and we're often going back into our data and correcting that as we go. So those are systematic errors. A random error, now get this, a random error is what remains after the mistakes and the systematic errors have been eliminated. So after we've done our best to get rid of our systematic errors, we are going to we're going to try to get rid of our, hang on a second, I'm trying to get my technology to work. Here we go. Almost there. I was just trying to underline something, and you know how Windows can be so helpful. So these are the errors that remain after. They remain after our mistakes and systematic errors have been eliminated. So these things don't go away. However, we can make them smaller. These are things that are beyond our control. For instance, think of those days when you're out there in the winter and you're looking across a plowed field and it's a cold day, but you see heat shimmer. Oh, buddy. We're doing the best we can to try to see through that. And we know that there's going to be some issue with our aiming, our pointing. We also know that with the GPS rover, the bubble in the circle, it's still got a little slop in it. So we do the best we can. And the issue is we can't measure these and we can't quantify them. They are what's left of the error we've got when we've tried to be as consistent as possible. The good news is they tend to be small and compensating, meaning that they tend to cancel each other out. Really, really handy for us. And the laws of probability that we'll get into here in a little while definitely govern these. So the majority of our random errors will be small, and good methods make those even smaller. So we said they tend to cancel out. Well, why is that? Because positive and negative errors are going to occur generally with the same frequency. Now, minor errors are going to occur more often than large ones. In fact, we use terms like outlier to describe the really large ones. Why? Because we know they don't occur very often. Okay. In fact, we'll see in a little while, the outlier really may be a blunder, is most likely to be a blunder. And to be honest, probably needs to be thrown out. That is, when we have a blunder, we don't want it to taint the rest of our data. We want to eliminate it, and we improve our quality when we do that. It's a small risk when we take out are really, really large errors that we believe are random, but they're probably blunders. And then, of course, those blunders, those outliers rarely occur in the grand scheme of things. So when we are reducing systematic error, when we make systematic error go down, what are we doing? We are increasing our accuracy. And when we reduce our random error, what are we doing? We are improving our precision. So if you can start to relate accuracy means the elimination of systematic error, and precision means the minimization of random error, then you're starting to get the distinction. Those two concepts, accuracy and precision, are paired with systematic error and random error. Now, you may already know this. You may be comfortable with this, but there are probably people in your organization that haven't yet grasped this. And so I want you to share this, especially with your field crew. They may not be thinking about it much. Some of them are. Some of them probably need some coaching. So I share this with you, hopefully that you can pass it on. And just to kind of summarize the big picture part of this makes sense. Mistakes or blunders, they need to be removed. They will skew or taint our data. Systematic errors must be corrected. And in a lot of cases, we can eliminate those with proper calibration. But even then, we may have to apply calibration data to something we cannot physically adjust. We take our calibration data and adjust our error, correct the data. And then random errors, we can never eliminate, but we can certainly work to minimize those. Well, as we move forward, we're going to be getting into some formulas that describe some relationships between inputs and the resultant errors. So you will see in some of the formulas we use the term capital E, and E is a general term for error. Now, there are multiple expressions of that error, and one of the most common is standard deviation. We'll go into that here in just a little bit. But please remember, standard deviation is only one type of expression of error. There are, the 50% or the 90%. You could pick any other percentage error and use that as an expression. And in fact, we've got a couple listed here. Circular error probable is another expression. One that we will definitely use today is the distance root mean square error. Those are all expressions of error. So I want you to think of E as the generic term, and all of these others are more specific terms. And each one of these is associated with a level of probability. And that will be one of the defining characteristics that separates them. That's not the only characteristic, but it's one of the predominant ones. So when you see E, understand we could be substituting standard deviation in for that, or distance root mean square, or something else. So let's deal with a little review, or it could be introduction for you, and that is some core concepts on standard deviation. What I have is a very simple computation here, and the scenario is that we have measured some line with a tape like you see here. Some of you are thinking, wow, that one's never been used. It doesn't look dirty or anything. Well, yeah, it's off of the Lufkin catalog, but we're going to be measuring with a tape, and we believe this to be very close to 100 feet long. We're going to measure the distance, And in fact, we're going to measure it 10 times. Well, why 10 times? Well, you've heard the term measure twice, cut once. Now, we've all been in the situation where we've measured once and we cut twice, or maybe 3 times. Well, that gets expensive after a while. And not only are we trying to determine the length of the line, but we're trying to find out the quality of our measurement. And what we'll see is when we repeat, when we get into redundant measurement, our quality goes up. Well, you and I are in the business of quality measurement. Not everything has to have the same quality. Some things we have to be very, very confident in. Why? Because not only are we in the measurement business, but we're also in the risk management business. That is, if we want to reduce our risk, we increase our confidence. We reduce uncertainty. Reducing risk, reducing uncertainty reduces risk. That's why we tend to be very, very careful when we're laying out column lines. And some of you remember, laying out column lines with a transit and a steel tape like you see here. So let's go ahead here. We're going to measure this thing 10 times, and we need to think about how are we going to get that rough estimate of the truth. Now, hopefully it's going to be a pretty good estimate of the truth. And we've taken care of all our systematic errors. In our case here, we have taken care of our tape temperature, tape sag, tape tension. We've got a brand new tape. We know it's calibrated. We've checked it ourselves. So tape alignment and elevation of the ends of the tape, the support conditions, we know all that. So we don't have our systematic error out of whack. We've accommodated all our systematic error. So now all we should have left is random error. And the mean of our results should give us what we're going to see here in a little bit is the most probable value. Well, there are other ways to describe the center of the data set, and the arithmetic mean or the average that we've talked about is the one we're going to use the most. When you've taken math courses, the mathematicians are obligated to help you understand how the mean is different than the median and the mode. And we're not going to use median and a mode, although I really do kind of like mode. I like my pie with some mode. I think they call that pie a la mode. And that's the only really kind of mode I am concerned about these days. And as a result, my weight is not stable, 250 and rising. It sounds like a forecast, but well, I hope that the rising stops at some point. But mode is not something we're going to use mathematically, but only in the culinary sense. So what we've done when we've created the average or the arithmetic mean, we've created the most probable value. Okay, and the first time I heard that or read that term, most probable value, and I wish I had read it or paid attention to it probably much earlier in life, it made loads of sense to me. It's the most probable value, meaning that we know it's probably not perfect, but it's about as good as we're gonna get. Well, then if you're trying to make that value even more probable, then it makes sense that you're probably going to add observations to it, aren't you? Okay, that is, if the average of 10 observations is 100 feet, like we see here, 100.00, if the average of 10 observations is 100 feet, well, we may feel pretty good about that compared to 2 observations that come out at 100 feet. You see, I could get 2 observations that come out at 100 feet, but which one do I have greater confidence in? Well, it's going to be likely going to be the one where I've got more observations. So as we dive in a little deeper, a standard deviation is the comparison of the individual readings that you've taken to the mean, the arithmetic mean of those readings. So Let's see what that really means. Sorry, what that indicates. The standard deviation really is a measure of the precision. Remember, we said precision is how tight a group we get. Well, when we're evaluating how tight a group we have, then we're saying how close are our results to each other. Well, now we've got a name for that relationship, that how close they are to each other, or we could say the spread of the data. It is the standard deviation. Now, first of all, please understand the operative word here is it's a deviation. They deviate from each other. Why is it a standard deviation? Well, it's the calculation from which we determine our other errors that we'll attach a percentage to. So it's kind of a building block for describing errors. It's not the only way to describe an error, but it is considered a standard way to describe the deviation in our data. Well, the difference between any individual reading and the mean of all those readings is what we call a residual. It's just a difference. Now, that residual is going to have not only a size, but it's also going to have a sign, whether it's positive or negative. But you'll see here in a moment that that sign becomes a problem. So in order for us to really get a feel for the spread of the data as we calculate a standard deviation, we have to square those residuals. And we're going to take the sum of the squared residuals in our calculations here. Now, this little letter here, it looks like a V. If I remember correctly, that's a Greek letter, nu, N-U. So, we're just going to call it a residual. I'm not going to worry about calling it the Greek letter, but it's not really a V. Well, here are my 10 hypothetical measurements. Now, in my case here, I've made them very, very idealized, but you can see they all end in some increment of 2/100ths of a foot away from 100. In fact, 100 occurs, looks like about 4 times in this data set. So I've got these 10 measurements, and I take the difference between each reading, each measurement, and the mean. So the very first one, 99.96 minus 100 gives me a negative 0.04. And the pattern continues down the list. Some of these, 4 of them, have a 0 residual. Why? Because they coincide with the mean. But here's the problem. If down here at the bottom, if I say I want to add all those things up to see what the spread is, well, the sum of those is going to work out to be 0 no matter what, if I'm just taking the sum of the residuals. Well, why is that? Well, this goes back to what we said before. These errors tend to be small and compensating. You add them up and they zero out. They compensate for each other. Why? Because they are centered around the mean value. The mean is in the middle of this range of data. So in order to get something that is non-zero, we need to make the positive and negative values go away. How do we do that? Well, simply by squaring those. So we square each residual to make the negative or positive value go away. And then when we sum them up, we get something that is non-zero, and it's non-negative. Okay, well, now we've got something, but you and I can look at that number and say it's just a number. Can't really visualize it. So what we want to do is create something that is more visual in nature, something we can relate to the spread of our data in not only a numeric sense, but in a physical sense as well. So what you see here is the formula for the standard deviation. Now, if you took a statistics class along the way somewhere, you probably remember, and this could be a bad memory, you probably remember there are 2 types of standard deviation, at least. And the 2 primary ones are the standard deviation of a population and the standard deviation of a sample. Well, this is the formula for the standard deviation of a sample. That's most appropriate for surveying because we are not dealing with such large volumes of data that a standard deviation of a population would be appropriate. So what you'll see here is from the previous screen, that term sigma, or the sum, we see the sigma and then the Greek letter nu squared. That's the sum of the squared residuals. The sum of the squared residuals is in the numerator over a denominator that is n minus 1. And n is the number of observations. Well, we had 10, then 10 minus 1 gives us 9. So that's all under a radical, and there's a plus minus out in front of this. So what we're saying then is the standard deviation, once I crank this out, is 0.023. Now the units, of course, are the same units of the basic measurement. So if we measured in feet, then our standard deviation is going to be in feet as long as our inputs are in feet. Okay? So let's then make sense of what this is. Every measurement then, the result of our 10 observations gives us one measurement. And that measurement here in our case is 100.00 because that's the mean, and then plus or minus 0.023. Now that plus or minus 0.023 is our uncertainty statement. It's not a guess. We've actually calculated that. We didn't scratch our chin and say, yeah, I'm guessing that's 0.0. No. We calculated it. Now, you've got to understand, though, this is not an exact discrete number. You see, what we now have is an estimate, and that's what statistics really is. Once I finally accepted this idea that statistics generates estimates, and those estimates really are ranges of possible numbers, then it's a whole lot easier to accept what I'm getting, because really we're saying the truth is somewhere in the range between, well, what would that be? That'd be 97.7, excuse me, 99.977. There we go. The range is between 99.977 feet and 100.023 feet. It's likely that the truth is somewhere in that range. The actual error could be smaller than 0.023, couldn't it? Okay, but it's an estimate of the precision. Okay, it's not a hard number. Now, let's relate this physically, or a little more graphically, I should say, to what we've got. We're going to develop what we call a histogram, which is really the basis of what we call the bell curve, or the normal distribution. And what we're going to do here is show the number of occurrences. Every little rectangle showing up here is an occurrence of a value. Okay, on the left you can see the values, and here we can see I had 4 occurrences of the value 100. I only had 1 occurrence of 100.04 and 1 occurrence of 99.96. Now, if we had, say, 100 observations, instead of having this notchy top to our histogram, we'd probably have something closer to this bell curve in red. But what I want to really have you pay attention to here now is the standard deviation does not cover the entire spread of the data. In fact, the vertical blue lines here on either side of the mean they go through what we call the inflection points of the bell curve. That is where the bell curve changes from convex up to concave up on either side of the mean. That inflection point coincides with the standard deviation. So what we'll see here in a little while is there is a known percentage of your data which we can expect to fall within the range of +1 to -1 standard deviations. All right, so let's take a look then at some examples. And really the question here, I'm going to compare this and another graph to help you understand the difference. We're looking for the difference in precision. You see, we said standard deviation is an indicator of precision. So here what I have is just a very hypothetical distribution of results. And that is, I've taken 100 measurements of a distance. It doesn't matter how I did it, but there's 100 measurements of this distance. The mean of this distance is 2,000 feet, 2,000.00 feet. I've calculated the standard deviation of these 100 measurements, and the standard deviation, using the methods we just talked about, comes out at 0.10 feet. So what that means on my bell curve up here is the mean would occur at the center of the bell curve, and there's a large number of measurements, of observations that fell at the mean or very close to the mean. Okay. And then there are a bit fewer observations that fell farther away from the mean at the standard deviation value. So the height of the bell curve here indicates the number of values that occur at that magnitude. Okay, so here you can see the purple zone is shown as, it's labeled as ranging from 1999.90 on the left to 2000.10 on the right. Okay, well, let's compare that to the next one. Here I've got another 2,000, maybe it's the same 2,000 foot different distance. And now I've got 100 observations of that one distance, but this time my standard deviation is plus or minus 0.04. Well, the question is, which of these two is more precise? Is it scenario 1 or is it scenario 2? I'm starting to sound like the optometrist, right? 1 or 2. Well, the issue here is precision is indicated by standard deviation, and the smaller the standard deviation, the smaller the spread in our error, in our data. The smaller the spread, the smaller the standard deviation. So that means the smaller spread is smaller random error. When random error goes down, that means precision has gone up. So it's this second of the two scenarios, not this one, but this one, which is considered more precise. Why? It's not because of the relative size of the error versus the measurement. It's the comparison of the two error or uncertainty statements. The first measurement had a larger standard deviation, therefore a lower precision because it had a higher error. Okay. So, whoops, went the wrong way. We said that minor errors occur more often than large ones. And what we have within the range of plus or minus 1 standard deviation are generally those minor errors. So the area within 1 standard deviation of the mean is about 68.3% of the total area. So what are we saying? 68, roughly 68 or 2/3, 68% or 2/3 of your data is going to fall within the range of plus or minus 1 standard deviation, either side of the mean, which also means that about 1/3 of the data falls outside of that. But you got to think about that. That 1/3 of that data, is it perhaps less reliable? Well, it very well could be. Very well could be. And we'll at some point we'll determine that, yeah, the stuff outside 2 standard deviations is probably going to be a blunder. Now, we said those large errors very rarely occur. They very rarely occur. So what we can then compute, and we'll see why in a little bit, is that the total area under the curve within 2 standard deviations of the mean, you know, it's -2 and +2, is going to be 95% of that sample group. So 95% of your values will fall within that range. Okay. So anything beyond that is going to be a fairly large error. Now we can take this a little further, and we can say that if this is 68% confidence at -1 to +1 standard deviation, then a 95% confidence comes from -2 to +2. Then we go one step further and we get 99% confidence when we go to plus or minus 3 standard deviations. If you've been paying attention to buzzwords in the business world for the last several years, you've probably heard the term 6 Sigma, right? 6 Sigma, it's kind of a buzzword for some, you know, business planning, business model kind of things. Well, what is 6 Sigma? It's this range that gives us 99% confidence. Oh, okay. It's kind of like, for a long time, everybody took, you know, the surveying term benchmark, and they wanted to use benchmark in every you know, business conversation they can. Well, it's kind of fallen out of style. And 6 Sigma, I don't know how big a deal that is anymore, but that's where the term comes from. All right. Well, let's think about not only 95% confidence level, but any other confidence level. You see, a confidence level helps us understand how much risk we are accepting or mitigating. So this curve, you're going to see this showing up in just about every surveying textbook worth having these days. For those of you who had Rayner, and then Rayner and Schmidt, and then Schmidt and Wong, and or have had Brinker, then Brinker and Wolf, and then Wolf and Galani, and now Galani, you're going to see this kind of thing in there. And so what we see is across the bottom, we have standard deviations listed. Let's see if we can do this. Here's one standard deviation, and it coincides that you go up on there on the curve, and where that vertical line hits the curve, well, that comes over and hits 68.27%. If we go to 95%, whoops, I got to be in the right place. Got too many screens I'm looking at. Sorry about that, folks. Come on. There we are. So 95% run over to the right, hit the curve, and go down. What we'll find is that 95% coincides with 1.96 times the standard deviation. But remember, these are estimates. If we're worried about 0.04 of a standard deviation, we're splitting that hair too fine, okay? Finer than is reasonable. So we round that to a factor of 2. Well, get this. If we go back to our 100.0 feet plus or minus 0.023 at 68% confidence, we can multiply that 68% error and get a 95% error. Multiply it by 2, And so 2 times our 0.023 gives us a value of 0.046. So get this. You do not have to remeasure something to calculate the 95% confidence level. It's simply a different expression of the same data, but at a different level of confidence. Okay. It's like casting a wider net. If I am trying to, let's say if I have a fish tank at home, it's usually because I got small fish in there. But if I take the little net that I use to scoop the little bitty fish out of the fish tank and I take it fishing and I'm trying to catch, a 2-pound bass, it's the wrong tool for the task, isn't it? So you match the confidence level to the acceptable, what is considered the acceptable level of risk. And we're going to see here in a little while that anything that we're serious about in the surveying world, we typically say we're using a 95% confidence level. Francis Moffat was also another widely read surveying instructor and author, and he said this, and many of you have probably his books on the shelf. If a measurement falls outside of 2 standard deviations, it's not a random error, it's a mistake. Throw it out. It's a blunder. Now, one of the reasons we bring this out, and this is the last thing for this particular session, so please come back for the second session here in just a little bit. But when you do an Opus report, and I hope all of you are using Opus as a tool, it's a wonderful, wonderful thing. If you're not using Opus, you're probably operating at a disadvantage, okay? You really need to learn how to use Opus. It's a wonderful thing. But at the very top of the Opus report, this is some data that our students ran last year, the students at Parkland College. And right at the very top of the report, it says all computed coordinate accuracies are listed as 1 sigma RMS values. RMS stands for root mean square. Well, that's what we're dealing with here, is these are standard deviations. 1 sigma, that's 1 standard deviation. So if you look here in the 2 red boxes, what you'll see is the standard deviations associated with the Earth standard, Earth fixed XYZ deltas in your coordinates in the 2 different datums, or in latitude, longitude, and ellipsoidal height, or even the standard deviation in the orthometric height as well. So this helps you visualize what is the uncertainty. So we're not just talking about a fundamental distance or an angle. Now, what you're starting to see here is that every coordinate has uncertainty in it. And that's a very essential concept we've got to deal with going forward.